Are there questions?
Last time when you were writing this small Hilbert space correlators,
Yes.
writing in terms of the large space correlators also extra.
Design, yeah.
But this was all you were doing it in the n sector, right? This was generally true.
Yeah, this is generally true, but I wrote down everything in the NS sector. So one sector I'll introduce afterwards. Yeah.
And
so
the fact that there is only one extra xi, I mean,
yeah.
But that is kind of related to the fact that you are working in the NS sector, right? I mean,
no, because see, the point is this xi, whether it's Ramond or NS, that information goes in whether the power of phi is half integer or integer. As far as the xi part is concerned, it doesn't care about NS or R, right? Because if you remember, xi don't carry JS operative, right? So they are not twisted in the Ramond sector. So from as far as the xi system is concerned, you can take it to be either in NS sector or in Ramond sector. Yes.
One point function of CFT primary is 0 unless weight is 0.
Yes. Okay. But you have some contradiction in mind or no? Yeah. So xi correlates, xi 1 point function is non-zero in the large Hilbert space, yeah, because xi weight is 0. Yeah. Okay. So now the first thing I'll do today is to describe how to extend these correlation functions to higher genus surfaces. Okay. And we'll basically follow the same kind of principle that we followed earlier, okay, which is by inserting a complete set of states. So let me remind you that we have said that if we have a correlation function like this, where these are complete set of states, phi r c, phi s. Okay. Each of these are complete set of basis states with these being orthonormal, delta rs. Okay. Then having a sum like this, okay, this is equivalent to correlation function on a real Riemann surface. With phi r say removed, and the identification which basically means that take a sphere. You can take it to a big sphere with some 1, 2 up to n, right? These vortex operators are sprinkled all over. Okay? And then you had these two, let me call this 3 to n, okay? Because so that there is a confusion between these. Okay, these are 1 and 2. So you take from 3 to n, 3, 4 to n, and here you have Z1 and Z2. Okay. And then the idea is that this sum is equivalent to cutting out unit circles around Z1 and Z2, okay, and making the identification that Z minus Z1 times Z minus Z2 equal to 1. Okay. Which means the following, that you take this circle and you identify with this circle, right? Because this means that if mod Z minus Z1 is equal to 1, then mod z minus z2 is equal to 1, right? So this circle you identified with this circle, right? With the phase appropriately adjusted, right? Because it's going in the opposite direction. The phase of this is opposite the phase of this. Now, as z becomes, suppose you are going inwards, right? When suppose z becomes less than z1, okay, or mod z becomes less than mod z, or maybe I should mod z minus z1. If mod z minus z1 is less than 1, this means mod z minus z2 should be greater than 1. Okay? So what this is saying is that if you move on the new Riemann surface along this line, right, so that you are approaching z1, it's as if you are coming out from this circle, right? So this is as if we have connected these two by some kind of tube, okay, these two, okay? And it becomes a homogeneous Riemann surface because this is like adding a handle to the original sphere. Is that clear? So this will generate a torus, okay? And the claim is that the correlation function on the torus is given in terms of the correlation function on the sphere by this formula. Okay, this is something we had discussed earlier when we were discussing how to extend the CFT correlation functions to higher genus surfaces. Oh, because imagine that it's like, imagine that we have two circles, you cut out these two circles and connect them by a pipe. That's a torus, right? So this picture is when the pipe length has gone to 0. Right? You have just taken this circle and that circle and sewed them with each other, right? And that topologically is a torus, right? Because you are adding a handle. No, it will generate a torus. And the surface that you get from the sphere, right? Z minus Z1 times Z minus Z2 equal to 1. This is a new surface, right? It's not a sphere anymore because you are making identification of points on the sphere, right? So on this circle is being identified with that circle, right? So this is a torus, the new object.
Where is tau?
Oh, where is tau? This is, yeah. So you can write the tau in terms of these parameters. I will not describe the formula, but in terms of the Z1, Z2, we can work out what tau is.
And on the torus, all the vertex operators are present there.
Exactly. Yeah. So it will not look like the torus in the usual coordinate system, right? Because Z coordinate is not the standard Z coordinate that one uses on the torus, where the identification is Z goes to Z plus 1 and Z goes to Z plus tau, right? So that's not the identification that we'll have. Here the two A and B cycles of the torus, right, will be, one A cycle will be like this and the B cycle will be like this. Okay, so A cycle, so let me draw this. So the A cycle will be something like this. And the B cycle will be when you go in here and come out from here, right? Because these two are actually same points because they have made this identification. And you can see that the A and B cycle will basically cut at 2 points, right? If you draw A and B cycle on the torus, sorry, not 2 points, 1 point. So it goes below this. It doesn't, maybe I should have drawn it in a different way. Yeah, so it's like a handle. So one cycle will be that when you go through the handle. Okay, you can draw it yourself. I'll not do this. So this is one cycle. Okay. And the other cycle will be, you see, this is going below the sphere, right? So our other cycle will be on top.
The red once it will go from below and come out from the outside.
Exactly. Yeah. Exactly. Yeah. Okay, so you can try to draw it and you can see that the A and B cycle will cut once, right? Not twice. That's what happens on the torus, right? If you have a torus, A cycle is like out on the outer circumference, you draw a circle, and B cycle will be like this, right? So it just cuts once on the outer circumference.
Chosen a different value for Z1 and Z2.
Yeah, that would matter. That will change tau. It will. So basically, the total number of parameters that you will get will be what you get for the correlation function of the torus. The sphere, for example, has 3 redundant complex coordinates, right? So that you have to take into account, right? So once you take that into account, you can see that the kind of torus that you get this way will be exactly what you get on the torus. The number of parameters will be the same.
But knowing it for one z, a given value of z1 and z2 is enough for a given tau.
For a given tau, yes, exactly.
The fact that the completeness relation is quadratic in nature, you will always get, if you start with this sphere, always get a closed surface, torus, and
yeah. You cannot put a boundary. Yeah.
Is there any way to get
boundary? You have to put additional data because that depends on what boundary condition you are putting, right? So just from the correlation function of the sphere, you cannot reconstruct the boundary data because there is an ambiguity of what boundary condition you are doing. So that has to be done separately. Okay, so now we are going to come to the xi eta phi system. Okay, so we want to build the correlation function of the xi eta phi system using the same principle. Okay. So in xi eta phi system, we introduce a complete basis. Two complete bases, in fact, pair of complete basis states. Phi r and phi rc such that okay. So here you see that if this has picture number q, this will have picture number -2 minus q. Okay, because we had said that on the sphere, the total picture number of all the operators has to be -2.
Phi is by definition is e to the power q phi or
It is built from e to the q phi by applying other beta gamma oscillators. Right? You can either use iota oscillators or beta gamma oscillators. It's useful to use beta gamma oscillators because beta gamma don't carry picture number, right? So if you want to use xi eta, then you have to keep changing q.
it is beta gamma accordingly and you e to the power phi.
Exactly, right? You can translate it into the xi eta language if you want. Is this clear? Okay. And if it has xi eta number, even if you apply beta gamma, you can always convert it into xi eta number, right? Because you just express beta and gamma in terms of xi's and etas and phi's. Okay. If it has xi eta number n, then this will have -n. The number of xi's minus number of etas, right? And here you are using the large Hilbert space, sorry, small Hilbert space formalism, small Hilbert space description, so that you don't count the extra xi 0, the extra 0 more that you need. Okay? So total number of xi's and etas should be equal. Okay, if you want to, you can also work in the large Hilbert space, in which case there will be an extra difference of a factor of 1. You need one more xi compared to eta. Okay, in the small Hilbert space, the number of xi's and number of etas are equal.
inner product is in small Hilbert space.
Inner product is in a small Hilbert space. Considering.
The number of sides should be equal to number of
Etas. Yeah. Right. So that's why I say if this carries net, say n extra xi's compared to etas, then this has to carry minus n. So n extra etas compared to xi. Right? So the total thing has equal number of xi's and etas. No, small Hilbert space is the space where the xi0 is removed. Right? The zero mode of xi is removed. Right? That you say that only those operators are allowed. That starting from the vacuum, you are not allowed to apply xi0, right? Because xi0 acting on vacuum is non-zero. Okay? But in the small Hilbert space, you don't allow xi0 to act on the vacuum. You see the only states that we'll be considering are where xi minus 1, xi minus 2, etc. can act on the vacuum, or eta minus 1, eta minus 2, etc. can act on the vacuum. Okay? So that's a small Hilbert space. We just remove, we don't. So in terms of operators, that means only those operators will be allowed which have xi accompanied by derivative. No xi without derivative, right? That's the definition of small Hilbert space. So this analysis we could do also in large Hilbert space, right? I have just chosen to do it in small Hilbert space. Okay, now you would expect that maybe the same description holds. If you now want to build the correlation function on the torus, we do the same thing. We apply this for correlation function on the torus. So torus correlation will be sum over R. However, there is a difference between what we normally do there and what we have to do here. And the difference is that this sum over R should be restricted to phi R having a fixed picture number in NS sector and another fixed picture number Q prime in R sector. Is this statement clear? So once you say phi R has picture number Q, of course phi RC is clear. Phi RC will have picture number minus to minus. Okay. But instead of allowing Q to be summed over, right, which is what we have normally expected, right, that to calculate correlation functions like this, you have to sum over Q. Okay. Here you don't sum over Q. Okay. You fix Q. Yeah, it doesn't matter, right? So that's the reason that you restrict to Q, because otherwise the same answer will be repeated infinite number of times. Okay, because every Q gives the same answer if you are willing to do analytic continuation. Okay, if you are willing to perform this sum using analytic continuation, which means basically that you have to use formulas like 1 plus x squared as 1 minus x inverse, even for x positive. If you are willing to use summation formulas like this, then you can show that the result actually doesn't depend on what value of Q you choose. So if you didn't restrict the sum over Q, you will get the same answer infinite number of times. And you avoid it by saying that you restrict the sum over Q to any fixed value.
The statement that for a given picture number itself, you have a complete set of.
Yeah, that's basically the statement, right? But this statement is somewhat misleading, right? Because suppose you are trying to do the same thing, not on a single sphere, but on two spheres. Here also you can insert a phi r and a phi rc, right? Okay. The rest of the operators are fixed, right? Have some fixed picture number. Okay. Here, if you say, okay, I choose my picture number of phi r to be whatever you like, right? That will not work because the total picture number here has to add up to -2, right? So here the picture number of phi r will be fixed, but it will be fixed by what else you have added. Okay. So it's still true that one picture number contributes, but that picture number has to be chosen appropriately so that you get a non-zero result for the correlation function. Right. Here we have a possibility of an arbitrary sum because if you take these to be q and these to be -2 minus q, the total picture number remains the same, right? Because q cancels. Okay, so you can in principle sum over all q. But the claim is that you have to sum over only one q if you want a proper correlation function. Okay. And this you can also trace to the beta gamma system. In terms of beta gamma system, it's easy to understand because from the beta gamma perspective, right, picture number is somewhat fake, right? Because beta and gamma didn't carry any picture number, right? So the fact that you have these different picture numbers is something that arose after bosonization. So if you are thinking in terms of beta gamma system and you are summing over a complete set of states, right, then you would not sum over different picture numbers.
You're saying because every value of q leads to the same answer. Then
Yeah.
sum over q leads to the infinite. I mean the average answer.
Exactly.
But it can happen, right? Every value of q leads to infinitesimal answer, and then in the end it's correct.
Well, but infinitesimal, you have to define the limit, right? If you sum over n picture numbers, you divide by n. Yeah, if you want to do it that way, right? Then you will get the correct answer. Right? Because every value of q gives the same answer, right? So you can use any arbitrary number and divide by n, right? So that will average out to the correct value.
But I mean, we can do that, right? And then those correlations can be derived by summing over q also.
But normally you don't put 1 over n in the sum, no? Because once you have orthonormalized, right? You say that you really have just this sum, right? Not 1 over n. So somewhere you have to make a choice, right? That this is somewhat different from what you normally would do. Okay. And the canonical choice that one makes is -1 and -half or -3/2. So the canonical choice is phi r -1, right? In that case, phi rc is also -1. Or phi r, this is in Ramon sector, this is in NS sector, this is in Ramon sector, phi r is -half, and this will mean phi rc is -3/2. And the advantage of these, as we discussed, is that you don't have to do this kind of analytic continuation, right? Because in these sectors, the L0 eigenvalue is really bounded from below. Because in these sectors, you can in principle evaluate the sum by just putting on a computer if you want to evaluate it numerically. Right? In any other sector, if you just put it on a computer and try to evaluate it numerically, you will not get a sensible answer, right? Because of this infinite sum over here.
I think I should have asked this. In the last class, you also mentioned that this is the canonical, right? Because it allows it allows you to do the sensible calculations, right?
Yeah.
But does it have any interpretation from the delta beta and delta gamma?
Yeah, it has an interpretation from the point of view of if you start from a gauge invariant formulation, right? where we had integration over the gravity nodes and so on, right? And there, if you say that you follow the same kind of logic, right? That we say that C, for example, has to accompany the vertex operator, right? If you use that kind of logic, right, then you can see that e to the minus phi, e to the minus phi by 2 has to accompany a vertex operator because it has to vanish, right? So if you demand, for example, that at the location of the punctures, right, the gamma should have a 0, right? Then these are really the current standard choices. Right? Because if you take any other choice, right, then you can make gamma vanish around one of them, but not around the other. Well, typically, I mean, if one of them you can do because it goes the opposite direction, right? Right? Because e to the minus 5 by 2 and e to the minus 3 by 2 both have negative values, right? So the gamma has 0. Okay? Minus 1 also the same. But 0 and 2, for example, right, will not have that property. 0 and minus 2, right? Minus 2 will be okay, but 0 will not be okay. Right? So anytime you are forced to have a positive Q, then you are in trouble, right? You cannot make gamma vanish.
Q and phi r c minus Q minus Q. So BA should not have any picture. Like vertex operator.
No, it came from here. This is a condition of phi r and phi rc, right?
So there, in that correlation, BA should have like sum up to 0, right?
Yes, indeed. Vi should have sum up to 0. Right? So what this is telling us is that on the torus, right, the total picture number should be 0 in order for the correlation function to be non-zero, right? So you can read out that from here. Right? Starting from the fact that on the sphere you need the total picture number to be minus 2, right? And this procedure, right? You can conclude that on the torus the total picture number should be 0. Okay, so let me state that next. That so on a genus G surface, on genus G, we'll need total phi charge two G minus 2 and total xi eta charge 0. If you repeat this analysis with the large Hilbert space, right, what we'll find is even on a genus G surface, the total xi eta charge should be 1. That means it doesn't matter what genus surface you are using, you will always need one more xi compared to the etas. Here, if you look at this, right, we concluded phi r and phi rc have total picture number minus 2. Because if one has q, the other one have minus q minus 2, right? Yes. So add them, right? Q plus minus 2 minus q. So these two together have minus 2. On the sphere, you have seen that the total phi charge has to be minus 2. Right? So this must have total picture number 0. Right? So that's the statement. That's what we saw. Right? So starting from the conservation law on the sphere, whole thing is on a sphere. Right? So starting from the conservation law on a sphere and keeping on doing pairs of circles like this, right, you can easily see that the total phi charge on a genus G surface should be 2G minus 2. Okay, every time you add a handle like this, right, you increase the picture number by 2, the required picture number by 2. Phi knows about it. Many things know about topology. Even BC knows about topology, right?
Yeah, I understand the reason First, because C is like the diffeomorphism, it's in one-to-one correspondence with the.
Yeah, here also it's like, I mean, you can reinterpret this as super diffeomorphism, right? That again, if you look at start from the wall sheet gravitino and graviton, right? The diffeomorphism means that not all degrees of freedom of the graviton can be fixed, right? There are some additional degrees which you have to integrate over, right? Those are the number of moduli, and that gives you the 6g minus 6. Right? In the same spirit, we can show not all components of the gravitino can be fixed. Yeah, there are some extra moduli which are called super moduli. Okay, and that's what is responsible for this extra 2g minus 2.
Can I do something similar? Like there we have this PP dagger operators.
Yes, you can do similar thing.
To
separate
out the things orthogonal to the diffeomorphism.
Yeah.
And those are called
Exactly. You can do similar there thing there, right? Because that is linearized fluctuation analysis, right? So you can do it for fermions also, wall sheet gravitons. Okay. But the point is the way we will formulate the perturbation theory eventually, right? In the case of bosonic string theory, we integrate over moduli, right? We have to finally integrate over those moduli. So if you follow this other approach that I just described, right, you should at the end integrate over the super moduli also, right? Which are the Grassmann odd variables. Okay. But so this is one way to formulate superstring perturbation theory. The other approach is that we imagine that we have done the integration over the Grassmann variables. Right? So imagine that you have integral d zeta, where zeta is a Grassmann variable. Right? How will you do the integral? You just need another zeta, right? Take the action in which is sitting in the exponent, okay? Pick linear terms in zeta, bring them down, and just do integral zeta d zeta zeta equal to 1. Okay? So basically what it is saying is that every time you do an integration over the supermoduli, okay, you will bring down some operator. Okay, that operator is what was multiplying the supermoduli in the action. So integral d zeta, so for Grassmann odd variables. Integral d zeta e to the power zeta k is just k. We call it chi. It's just chi. Right? So one way to formulate perturbation theory is that you leave the zetas unintegrated till the end, and you at the end you express the result in terms of integrals over the moduli and the zetas. Okay. The other approach, okay, is that you just do the integrals over the zetas, okay, and bring down the analog of this chi. So you will have, for every zeta you will have a chi, which you have to insert in the correlation function. Okay. So this is the approach you will follow, right? And we will also see what this chi is. Is this clear? I think this will be a good time to introduce what this chi is. This chi is called the picture changing operator. And it's given by the anti-commutator of UV with xi of z, okay, which you can also write this integral dw ab of w. This will be integration around, this means integration around z over contour surrounding z. Okay, that's the same as this, right? By the standard CFT procedure. Note that the BRST current also has a JB bar. Okay? But I have not included that because JB bar has no singularity in psi. Right? This is holomorphic. JB bar is anti-holomorphic, right? So in type 2 string theory, okay, we'll have both picture changing operator holomorphic and anti-holomorphic changing operator, okay, which are independent objects. Yeah, in the case of type 2, we'll have two picture changing operators. One holomorphic, one anti-holomorphic. Okay, because there'll be QB with xi bar of z bar. Transforms to picture changing operator. So this combination is the picture changing operator. I'll explain, yeah. Okay. And so let me write the expression for this first. So this is C del xi plus eta e to the eta e to the phi TF minus 1/4 Okay, this you can easily work out by knowing I have given the expression for JB, right? So you just have to use the OP of JB with xi, and you can check that this is true. Okay. Now, why does it have so? First of all, let's look at the properties. So it has picture number. So I has picture number 1. Okay, why? Because xi has picture number 1. Okay. Just to remind you why that is the case. So beta, you remember, is del xi to the minus phi. Right? This has picture number -1. Right? To the q phi always has picture number minus q. Right? There's picture number -1. Beta doesn't have picture number. So del xi should have picture number 1. Right? So this chi has picture number 1. Is that clear? Second, one might think that this is a BRST trivial operator. Okay, what do you mean by BRST trivial operator? The corresponding state is BRST trivial, in the BRST homology. Because you see chi of 0 acting on the vacuum. Right? This is the state corresponding to the operator chi, right? So this will be QB with xi of 0 acting on the vacuum. Okay. So which is QB with xi 0 on vacuum, which is QB xi 0, this is a 0 mode on vacuum. Is this clear? Okay. So this would indicate that this state is BRST trivial, right? It's QB on something in the large Hilbert space, right? The point is that this quantity is in the small is in the large Hilbert space, is not in the small Hilbert space. Okay? So this argument doesn't prove that this is BRST trivial in a small Hilbert space, because I0 on the vacuum is not a state in the small Hilbert space. Okay? So what one can show is that chi of 0 on the vacuum is a non-trivial element of a cohomology in the small Hilbert space. Is this clear? Okay. Now, I have not proven this, but at least one thing should be clear that this is a BRST invariant state. Because while it is true that this is not BRST trivial, if you apply another QB on it, it is certainly 0, right? Because QB square is 0. Okay. So this is BRST invariant. Okay. Now, in order to prove that it is really an element on the cohomology, you have to show that there is no other state that you can construct such that QB on that state is given by chi of 0 on 0. Right? This you can show, right? You can show basically by looking for states, okay, which have the right. See, this carries certain quantum numbers, right? In fact, it carries 0 host number and picture number. So if QB is acting on such a state like this, right? If this state happens to be QB on some other state, right? That should have a certain host number and a certain picture number. You can write a complete basis of states with that host number and picture number, and you can show that it is not possible to find any linear combination such that QB on that state is given by this. Is this clear? That's when you have a finite, when you are working in a finite dimensional Hilbert space, right? Checking whether it's an element of cohomology or not is reasonably straightforward, right? Because all you have to check is that you take an arbitrary linear combination in that finite dimensional space, act with QB, okay, and equate it to chi of 0 on the vacuum. Okay, and check that all those coefficients, that you cannot find those coefficients so that this equation is satisfied.
Okay, so we just want to check whether this chi of state is not a QB of some state, right?
Exactly. You have to check that this is not QB on something. And what I'm saying is that something, we already know that something has certain host number and certain picture number. Yeah, we know what that host number and picture number is. So you just write, and we also know the L0, right? So this has L0 equal to 0. That also you can check. Okay, in fact, it's conformal weight 0. It's a weight 0 primary because I was a weight 0 primary, right? And QB is an integral of the current. Okay? So it doesn't change weight 0 primary to anything else. So chi of z in fact is a weight 0 primary, right? So you have information about the L0 of the state, the host number and the picture number, and then you can check that within that subspace you cannot find any state which has this property that QB on that state is chi 0. Is this clear? So this chi, what it does is that it allows us to move between different picture numbers in the cohomology. Okay, so let me explain how that works. So let's suppose that V of z bar is an element of the cohomology with picture number Q.
This notion of small Hilbert space and large Hilbert space, this survives again this change in topology or not? Like
Or again, throw us.
Was only for sphere, right?
Yeah, but this survives in hard Hilbert space also. Basically, what you have to check is suppose you work in a large Hilbert space on the sphere, right? Then inside that correlation function, you have to insert a xi, right? Because you need one extra xi compared to eta. Okay? So you look at the conservation law that you get, okay? And then apply that to figure out what the conservation law on the torus and higher genus surfaces are. And you will find that in the large Hilbert space, you always have one extra xi compared to eta. Okay? Yeah, this is straightforward to see from this. What is not so straightforward to see is the fact that that once you take derivative of everything, right, except one, okay, then it becomes independent of the coordinate of that one. Right? That requires more effort to see this.
That is true, right? In higher genus also.
That is true in higher genus also.
Independent of zeta, not whatever.
Exactly. That's right. That once you take a set of zetas, say n plus 1 zetas and n etas, and take derivative acting on each n of the zetas, then the result becomes independent of the coordinate of the n plus 1 et zeta. Okay, and that's what allows you to construct the correlation functions in the small Hilbert space from the large Hilbert space. Right? Otherwise, you will be in trouble, right? Because if it depends on z naught, where you have inserted that a single xi, then you don't have a well-defined correlation function in the small Hilbert space. And from the path integral viewpoint, you can roughly see it as saying that on any genus Riemann surface, zeta has a single zero mode. Sorry, xi has a single zero mode, right? So in the path integral, you have to soak up that zero mode, right? So you need basically one extra xi to soak up that zero mode. But this also, okay, another point I should have said here, right, that this procedure that I described, right, the fact that you restrict to a single Hilbert Q, right, and instead of summing over Q, right, once you say that you fix Q, okay, we see that what now if you construct the basis states and a fixed Q, right, the phi, xi, and eta get correlated. Okay. Suppose you apply on eta minus 1, okay, on this state. That's the basis state, but that has a different picture number because eta carries picture number minus 1, right? 1, yeah, e to the minus, sorry, eta carries picture number minus 1, xi carries 1. Right? So that means that e to the q phi has to be made into e to the q minus 1 phi, right? Because total picture number has to be q, right, of all the basis states. Right? So now you see that when you choose this sum over R, right, that phi R basis, it's not that it's a product of what you do in eta and what you do in phi, right? But they get correlated, right? If you apply in eta, you have to change the corresponding q to q minus 1. And this is essentially the reason why the correlation function on the higher genus surface don't factor between xi eta and the phi system. Okay, it has, if you look at the correlation function, which is a complicated form, but you can see that there are terms in the correlation function which have non-trivial dependence on the arguments of xi eta as well as phi, right? And you cannot write it as a product. Okay, so this is one way of seeing why that is the case, right? That if everything was factored on the sphere, right? How can it be that when you do build up correlation functions, that it is not factored on higher genus surface, right? And the reason is essentially this, that you restrict to picture number, right? So what oscillators of xi eta we apply on the vacuum is correlated with what vacuum we should apply it on.
At the correlation level, the zeta, xi and eta was factorized with phi.
Yes.
Simplify is the calculation of this correlation, right?
Yes, true.
Right?
Yeah, on higher genus, this is not, you cannot do this, right? Fortunately, there is a paper of Hardlinder which has given the correlation function of xi eta phi system in arbitrary genus.
But did they start from genus?
They just wrote down the answer from some place. It's not clear how they got there, but there's an answer, right? And this has been tested because one can check all of these properties.
But if it's practical to compute, let's say, at torus, then the best way to is compute a pair and then do this.
Yeah, I mean that's a practical. Okay, I don't know whether it's practical, but it's algorithmic, right? That you can do this algorithmically. Exactly.
Summed over Q.
Yes.
Then the factorization would be clear, or not, between phi, zeta, eta.
If you summed over, but that's an infinite sum, right? So it will be ill-defined.
But
In principle, but that conclusion that it factors will not be true, right? So it basically means that these things won't commute, right? So the other way will be to not look at the xi eta phi, but beta gamma and delta beta delta gamma. Right? In fact, this is the way Witten did it. I mean, there is a 2012 paper in the appendix. He calculated the correlation functions of the beta gamma system of product of beta gamma and delta beta delta gamma, right? Just by requiring that beta correlation function and gamma correlation function has to vanish at the location of delta beta and delta gamma, right? and the stress tensor, right? You use the stress tensor of the beta gamma system. Okay. And that result, okay, whatever you got, agrees with the Verlinde answer. Okay. However, there is one point which is explicit in the Verlinde answer, which is not explicit in the Witten's answer, and that is the following, and that this fact will be important for us later. Okay. And that is the following, that when you are saying that you have del xi, right? You said, okay, large Hilbert space has only del xi, right? No xi. Okay. So why not just, sorry, small Hilbert space has del xi, no xi, right? So why not say that, okay, we just forget about xi altogether, right? And always work with correlation functions of del xi, eta, and e to the phi, right? Writing it as del xi, right, has the property that this makes it manifest that if you take 2 points, z1 and z, non-singular points, okay, and if you integrate del xi from z1 to z, okay, the result should be independent of the path, because it's I of z2 minus I of z1, right? And it's not just a formal argument, because in the Verlinde paper, there is an explicit formula for such correlation functions, right? They wrote the answer in the large Hilbert space. So they have the result for arbitrary sets of xi's and etas, okay, with one extra xi. So this fact that the integral over del xi, okay, is independent of the path, okay, is manifest when you think of the large Hilbert space, the small Hilbert space, as a restriction of the large Hilbert space, right? Because then it's really derivative of xi that you are integrating. Okay, so this integral z1 to z2 should be is independent of the path. But suppose we define del xi as limit z goes to w, but e to the eta of z, right? This is like because beta times delta beta. This is perfectly valid definition. If you knew the beta gamma and delta gamma correlation, you can always calculate the del xi correlation function this way. But this doesn't make it manifest that the integral of this from z1 to z2 will be independent of the path, right? Because this is now it's not del of anything, right? This is just defined in abstractly in terms of OP of beta and delta beta. So while it is true that if you actually check this, you find that it is independent of the path, right? But it's not manifest in the formulation where you work with beta gamma and delta beta delta. If you do the integral, you will find it's independent of the path. It's the same way, because the result is the same, right? So whatever Witten's method gives is the same result as Verlinde, except that the Verlindes give something more. They give the result in the large Hilbert space, right? Arbitrary number of xi's and etas. Okay.
If you allow ourselves only to work in, let's say, integrated code, the correlation which whenever delta zeta comes, it comes with an integral. And I'm sure whether it's
no, that is not necessarily true, right? You are thinking now of a contour integral, right? But sometimes del xi may come in inside a vertex property, you have to be a two-dimensional integral, right? And it may multiply by other things. It might be del of anything, right?
But what is the upshot here?
Upshot is that having the large Hilbert space in the background in your mind helps to get certain results which are not obvious if you work in the small Hilbert space from the beginning, right? The fact that the del xi correlation function is the derivative of xi, the derivative correlation function of xi, right, gives you some extra information that its integral is independent of the choice of path, right? And that is not obvious if you didn't know that del xi is del of something, right? Even though that something is not physical, right? That's part of a large Hilbert space which you don't want to work with. Okay? But that has this consequence that it tells us that integral of del xi between z1 and z2 is independent of the path.
This I cannot
at least not obviously. If you use the beta gamma, delta beta, delta gamma, right? Then as I said, you can define del xi in this way. But then it's not clear. See, given a current, suppose you have some dimension on object. From that perspective, del xi is some dimension on object, right? That you get by taking this OPE. This has dimension 1 that you can easily verify from this definition. If you take a dimension 1 object and integrate from Z1 to Z2, it's not necessary that it's independent of the path, right? You may go around, suppose that the two different paths enclose a point where there's a source for the dimension 1 current, right? Like e to the ik dot x, take del x, and take e to the ik dot x, right? If you take integrate del x around a contour, and if you take two contours which go around the two sides of the point where e to the ik dot x is located, the result is different. So this information is useful, right? Although it's not a new information, right? It's there hidden, of course. I mean, that's the same because the correlation function is the same. Right? Whether you calculate it as a derivative of the small Hilbert space correlation function or just in terms of beta gamma system, right? Beta gamma, delta beta, delta gamma, there is the same correlation function. Is that this fact is not manifest in that form.
How is it bypassed in large Hilbert space? That is not clear.
Yeah, I mean, the deeper understanding is not quite clear. I mean, you can say, why does large Hilbert space exist in the first place, right?
No, but how is it resolved?
Oh, yeah, because in large Hilbert space, we know the correlation function of xi's and etas.
So we can just take the derivative there and.
Yeah, and the xi's and eta correlation functions are single value, right? So integral of del xi from Z1 to Z2, you can also write as xi of Z2 minus xi of Z1, right? And there the path information has disappeared, right? Once you write it as xi of Z2 minus xi of Z1.
Okay, it's the single valuedness of xi.
Exactly. The single valuedness of xi correlation function in the large Hilbert space
That ensures this.
that ensures this property. Right? And the fact that the xi correlator is single valued, right, is obvious from the formula that Verlander wrote. Right? They have a single valued correlation function. It has many other, I mean, strange properties, right? It has singularities at points where there's no operator inside it. Right? So those features are there, but it is single valued.
Eta, epsilon, phi, all these, they have different picture numbers.
Hmm.
When you put them even on a sphere, they have to add up to picture number -2.
Yes.
Then on higher genus, it changes to some other value, like 2g minus 2.
Yes.
What else is the?
Oh, what changes is the following: that if you take, so suppose you have picture number -1, right? Suppose you have decided that we look at picture number -1. Okay. So let's look at the kind of basis states that we'll get in picture number -1. Right? One is this -1 itself, right? Which is e to the -5 on 0 acting on the vacuum. And now you can apply beta and gamma oscillators on this, for example, right? Take gamma. Okay? So gamma, whatever, gamma half, gamma -half, or -1, right? Okay. This you can check is given by gamma is eta e to the phi, right? Gamma is eta e to the phi. So this will give you eta -1 acting on vacuum. Right? So the phi charge has changed. This here phi charge was -1. Here the phi charge is 0. Right? Eta charge has compensated. The picture number is fixed, so eta charge has compensated for that, right? But when you construct the basis states, right? In the basis states, you have to allow this and this in the same basis, right? So what we see from here is that you couldn't independently change the phi charge and eta. Right? The basis, the choice of basis, right, correlates the phi and eta system. Yeah, then if you change the phi charge, you can compensate by corresponding eta charge, eta xi charge change. Right? So the basis that you have is no longer factored between the phi basis and the eta xi basis. If it was factored, then the correlation function will factor. Right? But that is not true anymore. Is this clear? Okay, so what does chi do? Let me, this is what I was going to say. So let's suppose that V is an element of the cohomology. Okay, and this basically means that we can throw away from V all that terms which are not L0 equal to 0. Okay, because this proof goes, if you remember, I had shown earlier that if we have a state that is in the cohomology, okay, you can, it has to have L0 equal to 0, right? L0 not equal to 0 states which are in the cohomology are BRC trivial. You remember that proof, right? You basically apply S if QBS is 0 and S is QB B0 on S with 1 over H, right? Okay, L0 on H, S is H. If this is a conformal weight, then this state you can write it this way, right? And QB on S is 0, so this is 1 over H, QB on B0S. Right? And this will basically tell us that as long as H is non-zero, it's QB on something. Right? So SBR is trivial. So if V is an element of the cohomology, we can take this to be dimension 0, 0. Now take the OP V I of Z V of W. Okay, V is the element of the cohomology of picture number Q. Did I say some picture number, right? Yeah, picture number Q. This I can expand as Z minus W to the minus N some O1 of W bar plus Z minus W equal minus N plus 1 O2 W bar. And then there is a term Z minus W to the 0. Let me call this O minus N plus 1. So ON, sorry, O0, O0, 1, ON, W bar, plus higher order terms. This one has dimension 0. Is that clear? Because this is dimension 0, this is dimension 0. Right? In the product, we pick up the coefficient of Z minus W to 0. So these are dimension 0. And using the fact that the QB, you can take the anti-commutator of QB with this product. Okay? And using the fact that QB on chi is 0, the QB chi this is commutator because chi is bosonic, V is bosonic. Okay, so using the fact that QB chi commutator is 0 and QB V commutator is 0, okay, you can check that QB with when is 0. Commutator of QB and QB with V is 0, right? So then QB with every one of these would be 0, right? Okay, so QB with ON will be 0. Okay. And this tells us, okay, this I have not proven, but this can be proven that when actually is an element of the cohomology. It's not BRST trivial. As long as V is not BRST trivial, one can show that when is not BRST trivial. So this generates a new element of the cohomology. Yeah, that if V is in the cohomology, right, which means that V is not BRST trivial, then when is also not BRST trivial. Right, that's the statement. Okay, that statement requires a different kind of proof, which is called the inverse picture changing, but let's just accept that for now. Okay. So this then tells us how to go from one element of the cohomology to another element of it. Yes.
Like O0 commutator.
Yes, but O0 has dimension n, right? So it will be RSA trivial, right? Yeah, so it is true that all of these have vanishing commutator, right? But others will be BRST trivial by that argument, right? Only the O0, ON has the chance of not being BRST trivial, and you can show that it is not BRST trivial. Oh, that is easy, because this one has picture number 1, right? So if he has picture number Q, this has picture number Q plus 1. Right? So ON has picture number Q plus 1. Yeah. So what this is telling us that using the picture changing operator, chi, we can map an element of cohomology in picture number Q to an element of the cohomology with picture number Q plus 1.
And so similarly, this is raising and the one with the eta will lower, right?
Yeah. So that we have to find an appropriate operator, right? Which is first of all BRST invariant, which is not BRST trivial, and which changes the picture number back, right? Which reduces picture number. There is an operator, right, which we can write down. I'll not describe that. Okay? But the claim is that just like chi raises picture number, it maps elements of the cohomology to elements of the cohomology of one higher picture number. There is a similar operation which lowers picture number. Okay? But that operation works only at generic momentum, because that makes use of momentum, okay, non-zero momentum. So at a generic momentum, this time I'm talking about momentum in the X space, right? The standard space-time momentum. Okay? That for a generic momentum, okay, this chi operation and the inverse picture changing operator, okay, together can be used to show that the cohomologies in every picture number are identical.
Cutoff, right? That picture number, it can that after a point you can't change the picture number.
No, there's no cutoff. Yeah, but this basically tells us that we can just restrict to one picture, right? Because the physics is the same.
That there is a picture number, there is a corresponding element. If I choose a picture number Q,
Yes.
in any other picture number, there is a corresponding
Element, exactly.
And but how does it?
Yeah, so I have not shown that the corresponding correlation functions will also be the same.
Yeah,
that also one can prove, right? Again, for generic momentum, that the correlation functions are the same. Right? I think once I explain how the correlation functions are calculated, it may become clear. But the claim is that it is true that so that you can represent, you can choose any picture number and quick representative in that picture number. Okay? And it doesn't matter what picture number you choose, right? But you have to fix it once and for all. Okay? And then the correlation functions that you calculate in one picture number will be the same as in any other picture number.
But this argument is better than the one which we gave about analytical continuation.
Yeah, but this argument is on only for the physical state, right? Yeah, this is certainly better than that one, because that I didn't really explain very well. Okay? But that one was a statement not necessarily for physical states. Okay? Now you are talking about the correlation function of the physical state, that it doesn't matter what picture number you choose, you get and end up with the same correlation function. Okay, in fact, not the correlation function, the integrated amplitude. The correlation functions may change, right? But the amplitude involves integrals. Right? After the integral, then you can show that the results are the same. Is this clear?
There is an issue with zero moment.
Pardon?
It needs zero, non-zero moment, right?
Yeah. So at zero momentum, you can show that there are examples where you can show that the homologies are not equal. Yeah. So there is a paper by Barkovits and Zoibach. I think that title of the paper is quite explicit, so I don't remember the reference, but you can figure it, we can find it. Okay, but zero momentum sector is special. For scattering amplitudes, you don't worry about zero momentum because you always can work with some finite momentum on the external states. And again, there is a canonical picture number that one uses here. So the canonical choice is -1 in NS sector and -12 in R sector.
You think the process like which goes as vacuum to vacuum or something, if there is
Yeah, exactly. But I mean, in normal S matrix, right? The zero momentum is, I mean, somewhat singular object, right? So you don't worry about zero momentum external states, right? If you are only interested in calculating S matrix, then this is good enough, right? If you are interested in something more, that suppose you want to give a vacuum expectation value of something, right? Then you go to zero momentum fields, right? There you need to use some off-shell formulation anyway, right? Some string field theory kind of argument. And from string field theory perspective, these are the standard choices. These are the choices you have to make. Because as I said, once you go off-shell, then this fact that the L0 is not bounded from below, right, becomes important because things which are propagating in the loop are off-shell states. Okay? And there it's really important that you work in these picture numbers. Okay, you can also use -3/2, but not anything more. In some sense, I mean, once you construct string field theory, the -12 and -3/2 play symmetric, right? You need both to formulate the theory.
But their picture number changing operation does not make sense at all, right? I mean,
in Ramon sector.
You can't, if you change your picture number, it's not physical anymore, right? I mean, in the off-shell formulation.
Yeah, in the off-shell formulation, the string fields from the beginning, right, are forced to have picture number -1 and picture number -12 and -3/2, right? So they are the string, you don't even have string fields carrying any other picture number, right? So you'll not see them. Okay, so next time we are going to discuss the cohomology in some more detail, the representative elements, for example, in the NS sector and R sector. Okay, but let me just say now what the role that the picture number plays in constructing correlation functions or amplitudes. So amplitudes. So this is almost the same as in the bosonic string theory. with one difference. With one difference. Okay, and I'll explain the difference, but first let me just say that what would go wrong if it was exactly the same. Okay, suppose it's exactly the same as in bosonic string theory. So then you take a Riemann surface. Put the vertex operators. Calculate the correlation function, insert those b's, right? You remember in the case of bosonic string theory, you also have to integrate, insert those integrals of b's, right? For every modular integral, there's a bi, right? It's like dmi bi, that combination comes together. You follow exactly the same procedure, you can do that, right? And you can set up this calculation as if you are doing the calculation in bosonic string theory. But suppose there are m ns sector and n r sector states. Then the total picture number that will carry, total picture number is minus m minus n by 2. Right? N is also, of course, always even, right? You cannot have odd number of fermions in an amplitude, that will just vanish, right? So n is even, so this is an integer. Okay. But we have seen that we need 2g minus 2 to get a non-zero answer. Right? So in general, the result will vanish if we try to repeat exactly the same thing that we did for the bosonic string. So the extra bit that you have to do will be to insert picture changing operators to compensate for this mismatch. So we insert 2g minus 2 plus m plus n by 2 picture changing operators. Yes.
So I thought the picture changing operator should not change that, right? The observable quantity.
Yes.
So why it looks that without applying the picture changing operator, you are getting zero.
Yeah, the reason is that you had these hidden supermodular integrals, right? And that number is exactly this. Okay, it has 2g minus 2 on an empty Riemann surface, but if you insert the vertex operators, you also have to demand that chi vanishes at those locations, and the total number of picture changing operators, total number of supermodular integrals is this many, right? So you have integral over d xi1 to d xi that number, right? Or d zeta 1 to d zeta that number. If you don't bring down anything from the exponent, imagine that you declare that I just do this integral, that will give you 0. Right? So you get a non-zero answer, you have to bring down linear terms from the exponent. And each time you bring down such a linear term, you are going to get a factor of chi. Right? So physically, that's the origin of this picture changing operators. Right? They are coming from the integration over the hidden supermoduli. Is that clear?
That's not variable. That's why it always gives you one.
Yeah, it just gives you one insertion, right? The zeta multiplies that picture changing operator, and that's what you insert. So this is the result of supermodular integral. And then the question will be, where should we insert this picture changing operators? Right? Because picture changing operators can be inserted anywhere on the Riemann surface. Right? So you have some product of the alpha equal to 1 to this number, 2g minus 2 plus m plus n by 2. We call this y alpha. That Grassmann even.
You say that you can insert it anywhere, so what?
Yeah, so you have picked some points y alpha, right? And you can insert it almost anywhere. Okay? One can check, one can show that the integrated result is independent of y alphas under certain condition. Okay, these conditions I'll discuss later. Okay, so these choice of y alphas are essentially, I mean, this amounts to what kind of gauge you have fixed on the in the supersymmetric part, right? Because if you recall that while doing the modular integral, right, you used a covariant gauge fixing, right? The gamma alpha beta, the worldsheet metric you fixed it proportional to eta alpha beta, right? There is similar gauge choice for the gravity law, right? And basically that gauge choice translates to what these y alphas are. So as I said, this is all true under certain conditions, but one of the conditions I'll state now. Okay, if that condition is not satisfied, then this procedure has to expression has to be modified. Okay, which also I'll discuss later. Okay. And that is that the y alphas.
For example, n is 1, n is 0, and g is 0.
M is 1. Yeah, but 1-point function you don't calculate, right? On the sphere, you calculate 3-point function.
Point function. N is 2.
But 2-point function also you don't calculate, right? So 3-point function, any equal to 2 is still okay, right? Oh, n equal to 2, yeah, but 2-point function you don't calculate. Right? But there is a single example where this problem appears, and that is on the disk, not in the closed string sector. The disk 1-point function does make sense. And on the disk, the total picture number non-conservation is such that you don't satisfy. You cannot compensate by adding a picture changing operator. You have to use some inverse picture changing operator, right? Or you have to go to this minus 3 up. This comes basically in the Ramon sector, right? Ramon on the disk, if you use a minus half picture, right, basically has total this thing minus 1, right? And you need minus 2 on the disk. Okay, so you cannot go from minus 1 to minus 2 using picture changing operator, right? You need inverse picture changing. So what one way to resolve it is to use minus 3 of minus half picture. Okay? That has total picture number minus 2, and you can do this, right? But this I think I'll discuss maybe when I do open string theory. Right now, you don't have to worry about this. Right? In any physical amplitude that you want to calculate, you can always make do with picture changing operators. We don't have to calculate. It's naively it is 0 because of the SL2C, right? Okay, naively it is 0. There are attempts to make it non-zero by various regularizations, right? But naively, if you do calculation of the sphere 2-point function, it is 0.
Like changing picture number.
No, changing picture number will not help because the SL2C is underlying there anyway, right?
Yeah.
That's in a Virasoro sector. Right? Again, as I said, sometimes you can cancel 0 with infinity, right? but that requires some appropriate regularization. Okay, so the one condition is that y alphas, okay, that for this formula to be valid, right, just insert the picture changing operators and we are done with it. Okay. Y alphas must be independent of the mi's, must be independent of the moduli, must be independent of the moduli mi. Yeah, I think I don't remember if I called them mi or these are the 6g minus 6 plus 2n moduli. Okay, the boson usual bosonic moduli, right? That you have to integrate. The Riemann surface moduli plus the locations of the punctures. Okay. So you have a form in the moduli space. You are integrating over these mi's, right? And the point is, as you change the mi's, right, we have to make sure that the y alphas remain fixed. Okay. No, so that this formula is valid. This formula is not valid if the y alphas, there is a more general formula that I'll write down. If y alphas change as a function of mi, and in fact, it is necessary to do that, right? Because you cannot really keep the yi's fixed, y alphas fixed, as you will see. Right? The other conditions will force y alphas to vary with mi. Okay? But in that case, this formula will have to be modified. No, you can't just insert some product of chi's, right? And basically, physically, what's happening in that case is that now you are thinking of the moduli integral, the usual moduli integral and the supermoduli integral are factoring, right? You do supermoduli integral and then independently the moduli integral, right? But that need not be the case, right? In general, you may choose appropriate gauge sections to integrate over, where these two are coupled, right? How you choose a gauge may depend on how what the moduli are, right? How you choose a gauge for the gravity nose may depend on the usual moduli, right? At different points in the moduli space, you may choose different gauges. Right? That will correspond to y alphas being functions of mi. But in that case, the measure doesn't factorize into a measure over mi and a measure over the supermoduli. Right? You have to do more work. Okay? So I'll write down the answer in the general case when the y alphas do depend on moduli. Right? But as it stands, this answer, just insert this in the integral. Right? This is valid only for y alphas being independent of mi. No, this is all in small Hilbert space, not in large Hilbert space. Right? All the correlation functions we calculate in the small Hilbert space. We can use the large Hilbert space as the backbone, right? I mean, we can derive various properties of this amplitude. You can make use of the fact that there is a large Hilbert space, right? But the amplitudes are written in the small Hilbert space. Right? So you can think of the large Hilbert space as a convenient tool, right, which you can use if necessary. But the physical Hilbert space is the small Hilbert space, and every calculation can in principle be done remaining fully inside the small Hilbert space.
Operators are kind of written in an anti-commutator of an operator.
But I also wrote down another expression for the picture changing operator, right, which didn't include any xi. Right? That QV commutator xi, that second expression, right, had C del xi, right? Didn't have. So Q xi anti-commutator is actually in the small Hilbert space. Okay, so I think I'll stop here. So next time I'll first discuss the cohomology, right? That what kind of cohomology elements one can choose in the NS sector and the R sector. And then we'll try to go into details of amplitudes.